Welcome to the lecture 6 in the lecture series of FIR filter design. In the past lecture we have discussed about the design of linear phase FIR filters through windowing technique. In this technique, in that lectures we actually defined various kinds of windowing sequences, their features, their advantages comparatively with respect to the other windows, their mathematical definitions, their descriptions with respect to graphical through graphs, as well as we have seen some of those frequency domain characteristics of some windowing functions, and the details of their main lobe widths and the magnitude of their first side lobe levels. Also we have seen the implementation of a FIR low pass filter using all those sequences, and also calculated what happens to its pass band and stop band characteristics. With these points certainly in mind, now we shall move forward to deal with certain design problems in this particular lecture. First of all, I shall summarize the procedure of designing a linear phase FIR filter using a windowing technique. The procedure for designing the FIR filters using windowing technique is, generally in the design question itself, in the design problem itself, you will be provided with the desired frequency response related values. Sometimes it will be said as that they require a low pass filter or a band pass filter with certain specifications. That specifications will be already given, or else sometimes you will be giving you the specifications related to the cutoff frequency. Based upon that, you need to write the values of HD of e power j omega based upon ideal filter characteristics. And once we choose this desired frequency response, also verify what is the value of n and which kind of a windowing technique they are suggesting us to use in the design of this particular filter. Based upon the number of samples of the windowing sequence and the type of the window that what we are using, now proceed further in order to find out the inverse Fourier transform of the desired frequency response that what they have given to obtain the desired impulse response HD of n. This HD of n can be found simply by using this inverse Fourier transform formula, which we generally write as HD of n is equal to 1 by 2 pi integral of minus pi to pi HD of e power j omega into e power j omega and d omega. For limits of integration, we need to just check with respect to the problem itself. And once as we already know about the windowing sequence given in the problem, just choose those desired windowing sequence W of n defined between n is equal to minus n minus 1 by 2 to plus n minus 1 by 2, and multiply this infinite sequence that what we have got here HD of n to get a finite endpoint impulse response h of n. Once we get the required impulse response, then calculate the Z transform of h of n such that it will be a it will represent the transfer function of the filter. Generally, since our HD of n or the h of n that what we have calculated are spread on both sides of the axis, generally our filter will be a non-causal filter. In order to convert this non-causal filter into a causal filter, then multiply this hn of z or the h of z, that what we have got in the fourth step, just by multiplying it with z power minus n minus 1 by 2, we can convert it into a realizable causal FIR filter. Also, we need to use those symmetry conditions perfectly in order to get the desired response and the transfer function of the filter. And sometimes you will be asked to draw the frequency response or the magnitude response of the filter, and also sometimes you will also be asked to represent or realize this FIR filter using any structure. And you need to be prepared in order to perform those particular tasks too. And now let us start with some example problems on design of linear phase FIR filters using windowing techniques. Let us start the first one. And the first one is related to designing a linear phase FIR filter using a rectangular window by taking 7 samples of windowing sequence and with a cutoff frequency of omega c is equal to 0.2 pi radian per second. Here clearly the digital cutoff frequency 0.2 pi radian per sample was given, and he has asked us to use this rectangular window by considering the 7 samples of windowing sequence to design a low pass FIR filter. And let us, since so nothing is mentioned about the samples, the sample values, nothing is mentioned about the sample values. Now let us assume, let us choose a symmetric impulse response with symmetry condition as h of n minus 1 minus n is equal to h of n, that is, it is spread on both sides of the axis. And therefore, since we are considering a FIR low pass filter, the desired ideal frequency low pass filter HD of e power j omega can be written as e power minus alpha j omega minus omega c less than or equal to omega less than or omega c. That means between this given cutoff frequency or particular h of n, the impulse response of the system will be equal to 1, and remaining all cases it is going to be 0. When evaluated the system transfer function, generally the transfer function will be e power minus alpha j omega, because simply the output of that particular filter will be equal to the delayed version of the input sequence whenever we pass through an ideal filter, and in such case the relation between the output and the input is given in terms of the delayed version of input itself. Whenever we take the ratio of the transfer functions, the ratio of the frequency responses of the output to the input, generally it will be in the form of an exponential. I hope that everyone understand why HD of e power j omega is taken as e power minus alpha j omega. And now once we are able to fix this desired ideal frequency response for our FIR low pass filter, let us proceed further for the step 2 or step 3, where we are trying to find out the HD of n, the desired impulse response, by using the inverse Fourier transform relation and using the HD of e power j omega seen earlier. And now substituting the value of HD of e power j omega here, e power minus j omega alpha, within the given limits of minus omega c to omega c, and since omega c is given as 0.2 pi, it is certainly less than this pi, and that is the reason the integral limits are changed based upon the given specifications. But however, I haven't directly substituted 0.2 pi here, so we will be using those values a little later. And I write now the expression based upon the above 1 by 2 pi integral of minus omega c to omega c e power j omega alpha n minus alpha d omega. And evaluating this integral, we find that this can be written as 1 by pi into n minus alpha e power j omega c n minus alpha minus e power minus j omega c n minus alpha by 2 say, which leads to a sine function, sine of omega c into n minus alpha by n minus alpha into pi. This hd of n is acceptable for all values of n except n is equal to alpha. Whenever n is equal to alpha, this particular sine function or the impulse response becomes indeterminate. Therefore, in order to find out the value of hd of n at n is equal to alpha, we need to apply the limits on both sides and then find the value of h of n. Therefore, when n is equal to alpha, I substitute actually consider limiting limits on both sides, limiting functions on both sides. Therefore, when limit n tends to infinity or limit n minus alpha tends to 0, our hd of n value will be something like this: sine of omega c into n minus alpha by n minus alpha. This looks like limit x tends to 0 sine x by x in terms of some function sine 2x by x, wherefore this becomes simply 1. But since we do have a value of omega c, I multiply that 1 with omega c and we are left with 1 by pi. Therefore, we are writing it as omega c by pi. And since we are asked to use a rectangular windowing sequence in this case, now the rectangular windowing sequence is defined as WR of n is equal to 1 for n is equal to 0 to n minus 1, and therefore now the impulse response, or else it is also from n is equal to 0 to n minus 1. Therefore, the required impulse response h of n can be calculated as the multiplication of hd of n, the desired impulse response, with the windowing function, the rectangular windowing function given here. Since rectangular windowing function is simply equal to unity in all those cases for n samples, therefore this can be simply written as hd of n for n is equal to 0 to n minus 1. Now the calculations part for h of n, the finite impulse response sequence, can be calculated based upon the values of n that is given. Since we are asked to find out for 7 samples, I am identifying those 7 samples as 0 to 6, and h of n is now simply equal to h of minus n in this case, or h of n minus 1 minus n in this case, and therefore n is equal to 0. When I substitute n is equal to 0 in the above equation of the impulse response, that is hd of n is equal to sine of omega c n minus alpha by n minus alpha into pi, I get that value of h of 0 as 0.1009. Similarly, for n is equal to 1, 0.1514, and for n is equal to 2, 0.1871. These values are pretty much straightforward after substituting the values of n and substituting the values of n minus 1 by 2, and just calculating the sine values, we will be able to get these values. However, at n is equal to n minus 1 by 2, that is equal to 3 in this case, we have already seen in the case of n is equal to alpha that value of h of n is simply equal to omega c by pi. Therefore, substituting this omega c value, which is equal to 0.2 pi given in the question, and substituting those values, I get it as 0.2. Similarly, for all other values of the impulse response, n is equal to 4, 5, 6, exploiting the symmetry relation h of n is equal to h of n minus 1 minus n, we observe that h of 4 is simply equal to h of 2, h of 5 is equal to h of 1, and h of 6 is equal to h of 0. And since we have already calculated these values, I just substitute those values with this. And therefore, now we are successful in calculating the impulse response, the finite impulse response for n is equal to 0 to 6, and their corresponding values are given as these values: 0.1009, 0.1514, 0.18771, and so on. And we are able to observe the symmetry with respect to n is equal to 3, and h of 2 is equal to h of 4, h of 1 is equal to h of 5, and h of 0 is equal to h of 6. Now, trying to represent the transfer function of the system or the filter that what we have designed by using the Z transform definition, which can be written as Z transform of h of n and h of n is given from n is equal to 0 to n minus 1, h of n into z power minus n. Therefore, substituting the values of n, capital N here, and also the values of small n, and expanding this equation, I generally find it as h of 0 plus h of 1 into z power minus 1, so on until h of 6 into z power minus 6. As we know that based upon the symmetry, the values of h of 0 and h of 6 are equal, and therefore I take this as a common term and just prove this z inverse values together, and therefore we get this expression as h of 0 into 1 plus z power minus 6 plus h of 1 plus h of 1 into z power minus 1 plus z power minus 5, since h of 1 is equal to h of 5, and h of 2 into z power minus 2 plus z power minus 4, since h of 2 is equal to h of 4, and h of 3 into z power minus 3. Once this equation is formed, I just substitute the values of h of 0, h of 1, h of 2, h of 3 from the last calculations that what we have done, and I use these calculations in order to substitute here in order to get my transfer function. Since this purely represents a causal transfer function, there is no need to multiply with the z power minus of n minus 1 by 2 here. And proceeding further, in order to represent the structure of this particular designed linear phase low pass filter, there is a special kind of representation. It's almost like a direct form 1 representation of this particular structure. Therefore, I would like to convert this in terms of y of z and x of z, and identify this h of z as a ratio of y of z by x of z, and I cross multiply those equations, and therefore I get this equation as y of z is equal to 0.1009 into x of z plus z power minus 6 into x of z plus so on, and we are able to get this particular expression now. And based upon this expression, now I would like to draw or realize the filter structure in a pretty direct way. This is also called as a linear phase structure, and we shall go through this structure here in this case. Here, since this particular case is here we do have 6 delay elements. Since we do have 6 delay elements with respect to x of z, the highest power of delaying element is z power minus 6. Therefore, since they are symmetric in nature, generally the values of h of 1, h of 0, h of 1 and h of 2 are equal. Generally, we identify those delay elements something like this. Generally, they can be spread linearly. However, since these values are equal at some cases, I would like to use the adders and just represent this equation in a direct form. Since we require 6 delaying filters, I have drawn x of z with the 6 delayed versions of it as z inverse, and here it was equal to x of z, and here it is equal to x of z into z inverse. Here it becomes x of z into z power minus 2, x of z into z power minus 3, and when passed through this delaying filter, here it is x of z into z power minus 4, x of z into z power minus 5, and x of z into z power minus 6. Therefore, from the first expression in the transfer function, we observe that x of z and z power minus 6 into x of z are grouped together and multiplied with a coefficient 0.1009, which is a scalar quantity. I just multiply this something like this. I have added this x of z to x of z into z power minus 6 and then multiplied with the 0.1009 here. And subsequently here I do get it as x of z into z inverse plus x of z into z power minus 5, which is multiplied with 0.1514 according to this particular expression here. And similarly, x of z into z power minus 2 plus I have added this x of z power minus 4 and then multiplied with the scalar 0.18771, which is a coefficient in this case. And once we add all these expressions, I generally get and we are also left with one more quantity like 0.2 into x of z into z power minus 3, which is directly taken from here, multiplying with a 0.2. the scalar quantity, and therefore adding all these expressions, this results in y of z. That is why this is pretty much called as a linear phase structure of realizing an FIR filter. This is how you can realize your FIR filters whenever they are symmetric in nature, and you can utilize this linear phase structure so that it can be drawn compactly. And sometimes you might also be asked to go with the frequency response, and since we have chosen a symmetric and symmetric impulse response with odd numbered values from the tables that what we have written earlier in the features of our linear phase FIR filters, we identify this is a case 1 structure, and therefore the magnitude response of the case 1 structure is given as h of n minus 1 by 2 plus sigma n is equal to 1 to n minus 1 by 2 to h of n minus 1 by 2 minus n cos omega n. Substituting various values of capital N and small n, we do get our magnitude response in this form: h of 3 plus 2 h of 2 cos omega plus 2 h of n 1 cos 2 omega plus 2 h of 0 cos 3 omega. Substituting the values of h of 3, h of 2, h of 1, h of 0, this will be the resultant magnitude response of the filter. Now this is a cos omega, cos 2 omega and cos 3 omega. Just identify this as cos omega, there is a correction here. And now substituting various values of omega so that we can draw this magnitude response effectively, I consider around 12 samples or else at least 11 samples out of 0 to pi, and therefore I am representing this as 0 into pi by 6. I have considered 16 samples here between 0 to pi, and therefore I write it as 0 into pi by 16, 1 into pi by 16, 2 pi by 16, 3 pi by 16, 4 pi by 16, and different multiples of pi by 16 until pi. 16 into pi by 16 leads to pi 1, that is equal to 1 in this case, and therefore from 0 to 1 I have taken as many as 16 values and calculated those magnitudes of a omega in this case, and I was able to see the magnitude response of our the frequency response or the magnitude response of the linear phase FIR filter so far what we have designed. And in this case we are able to see that it is monotonically decreasing, and you are able to see that the values of the filter are also not they are all non-zero values in the stop band too. This is what we are able to observe, and you can directly calculate this by substituting the values of 0, 1 pi by 16 in the above expression: 0.2 plus 0.3742 cos omega plus 0.3028 cos 2 omega plus 0.2018 cos 3 omega. Different values of omega are substituted and then generally calculated, and calculated the magnitude of this, and we have also represented the absolute values of this, and therefore we are able to get in this fashion. This is how we can also plot your frequency responses sometimes. And in the above problem, what we have done is, first, based upon the given specifications, we have clearly written the desired specifications, identified the value of n, whether it is symmetric or not, and whether it is odd or even in the first step. And in the second step we have calculated the desired impulse response using the inverse Fourier transform equation. And in the third step, based upon the given windowing sequence, we have converted the non-causal impulse response filter, or else a infinite impulse response filter, into a finite impulse response filter by multiplying the suitable windowing sequence given, that is a rectangular windowing sequence given here in this case. And once we got the finite impulse response sequence, and then we have calculated the transfer function of the system, and based upon the transfer function of the system we then realize that structure, we realize the function, we realize this filter in a suitable structure, that is what we call as a linear phase structure, and then we have calculated the frequency response of the system. This is how you will be able to design your low pass or high pass or band pass and band stop filters whenever you are asked to do so with respect to this windowing technique, the use of this windowing techniques. Now let us proceed still further to see another example where we can actually design a band pass filter instead of a low pass filter or a high pass filter. Since high pass filter and low pass filter are almost the same, the design includes the same, but now I would like to calculate or design a band pass filter based upon some another windowing sequence. Okay, and let us move further. Okay, and I've considered example 2. In this case, we were asked to design a linear phase FIR band pass filter, and to which has a range of where the pass band frequency range is clearly given, that it is from 0.4 pi to 0.65 radian per sample. Since our particular equations are given in terms of our specifications are given in terms of radian per sample, I assume that they are the digital frequencies. If digital frequencies are not given generally, and if analog frequencies are given, then you need to convert them into digital frequencies based upon the formula. I think you know about that particular formulas, and where the formula is simply omega c is equal to 2 pi fc by fs, or else in this case omega c1 is 0.4 pi and omega c2 is equal to 0.65 pi in this case. And he has also clearly given that that we need to take 7 samples of Hanning windowing sequence. This is a class of raised cosine window. Therefore, we will make use of this particular windowing sequence in order to design a linear phase FIR band pass filter. Now, since it was clearly given it is a odd numbered sample, we choose that it is a symmetric impulse response with the symmetry condition h of n minus 1 minus n is equal to h of n. Therefore, it will be purely causal in this case, and therefore hd of e power j omega is equal to e power minus alpha j omega minus omega c2 less than or equal to omega less than or equal to minus omega c1. That is so we were mentioning the range of the passband frequency here, and outside this passband frequency we assume that it is equal to 0. This is the desired frequency response, and since it's an ideal frequency response, we generally write it in terms of omega as e power minus alpha j omega. And now in the second step, I am trying to find out the Fourier the impulse response using the inverse Fourier transform relation by substituting the limits from minus omega c to omega minus omega c1, and similarly from omega c1 to omega c2. I do find out the the inverse Fourier transform, and the inverse Fourier transform relation is given as 1 by pi into n minus alpha sin omega c2 n minus alpha minus sin omega c1 n minus alpha. And this particular expression for hd of n also still holds good for all values of n from minus infinity to plus infinity, but not at n is equal to alpha. And in this case, what we do is generally substitute and we will be trying to find out the value of hd of n at alpha separately by applying these limits on both sides. Therefore, applying the limits on both sides, I find that at n is equal to alpha, the value of hd of n is equal to 1 by pi into omega c2 minus omega c1. And so now in step 3, I am making this infinite impulse response filter into a finite one just by multiplying it with the given windowing sequence from 0 to n minus 1. It was identified the Hanning windowing sequence is defined as 0.5 minus 0.5 cos 2 pi n by n minus 1. I have directly noted it, and now I am multiplying my hd of n with this Hanning windowing sequence, so that I will be getting my h of n, which is finite in nature. And I write two expressions, since hd of n has two values, hd of n exclusively for n is equal to alpha, it is written as 1 by pi into omega c2 minus omega c1. Therefore I use this expression for n is equal to alpha here, and for all n not equal to alpha, generally I use this particular equation, the above equation that what we have got upon evaluation, and I use this for all n which is not equal to alpha, and substituting various values of n in order to calculate the finite impulse response sequence h of n. I substitute n is equal to different values of n from 0 to 6 in this case, and alpha is identified as n minus 1 by 2, which is equal to 6 minus 1 by 2, which is 3 in this case. And substituting all those values, I get my impulse response values as, for n is equal to 0, substituting all those values, I identify that it is equal to 0, and n is equal to 1, it is equal to minus 0.0556, and n is equal to 2, it is minus 0.0143, and n is equal to 3 for a suitable value. Whenever we substitute with the second equation that what we have seen in this case, I get it as n is equal to 3, it is equal to 0.25, and thereafter I use this symmetry relation, and I write n is equal to 4, which is equal to h of 4 is equal to h of 2, which is simply equal to minus 0.0143, and for n is equal to 5, h of 5 is equal to minus 0.0556, which is equal to h of 1 in this case based upon the symmetry, and similarly n is equal to 6, for h of 6 will be equal to h of 0, which is 0 in this case. Based upon the values of the impulse response that what we have calculated, now I write the transfer function of the filter in terms of h of z, which is represented in terms of z power minus 1 to z power minus 6, and therefore substituting these values, I identify the transfer function something like this. And now I also realize the structure of this particular transfer function, which can be noted something like this, where y of z is given in terms of x of z relations. By using the above transfer function form, I realize a linear phase structure for the transfer function defined below. Here, since the highest power of this delayed function of z is equal to z power minus 5, I assume 5 delay elements here, where this is the input. Here there is an input value of x of z. When passed through z inverse, we have z inverse of x of z, z power minus 2 into x of z, and z power minus 3 into x of z, and so on. Therefore, arranging them in the most suitable way where we can group them together, and I have identified the different parts where we can just multiply them, we can add them and multiply with the coefficients. Therefore, x of z into z power minus 5 plus x of z into z power minus 5, z power minus 1 and z power minus 5 are grouped together here and then multiplied with the coefficient minus 0.0556, and then added to all those remaining multiples and of the coefficients and all in order to get our y of z. I hope that you are able to understand the realization of the structure and the design of a linear phase FIR filter based upon the specification given. The frequency response of this particular FIR bandpass filter is left as an exercise to the readers, and I want you to practice that, drawing the frequency response of the filter based upon the equations that what we get. Another easy way of getting the frequency response is just by substituting z with e power j omega in our transfer function, and give some various values of omega, and then you can also plot the magnitude response based upon the magnitudes of what we get by substituting the omega values. That's all for this lecture, and you can also practice many other problems on linear phase FIR filter design by using this windowing techniques. Here in this lecture we have designed FIR low pass filter and band pass filter using rectangular windows and Hanning windows respectively, and that's all for this lecture. Thank you, and if you have any particular doubts you can comment in the comment section, Also, please do subscribe this channel for latest videos and for more updated videos on DSP. Thank you.